Hello, and welcome to our program, Astronomy for Everyone. The subject for this month's show is the Northern Lights. And here to tell us all about them is Mike Murray, Planetarium Manager and Astronomer at Delta College Planetarium in Bay City, Michigan. Mike, welcome to the program.
Hey, thank you for having me.
You're welcome. The Northern Lights are a fascinating sight for us here in the Northern Hemisphere, hence the Northern Lights. The folks in the Southern Hemisphere have their own. But we'd like to learn more about their story, how they happen, and any other good information that you've got for us. So the floor is yours.
All right, thank you very much. Well, like I said, it's really great to be here and to be able to join you. This has been an incredibly popular program for us, both up at the planetarium because we've done live shows about it in the dome, but we've also done some online programming, some live streams that were incredibly popular, even more than we expected. And so it's always fun to be able to talk about the Northern Lights and how you can find them. We're going to be talking about things like, what creates them. And we sometimes call them the Aurora Borealis. That's actually what Galileo named them. He was the one who coined the term. But they have fascinated people, of course, forever. So we're going to look at exploring their folklore, their causes and effects. And what you're seeing here is a time-lapse sequence from Tromsø, Norway. It's located at about 69 degrees north latitude, and this is one of the prime locations to see the aurora because you're almost directly underneath what's called the auroral oval. And of course, what is that? That's a part of what we're going to be exploring, and so we can find out just why it's that location as opposed to, say, the North Pole itself, and we'll talk about some of those latitudes. We've seen the Northern Lights reflected in legend and history and religion and art all through the ages. One of my favorites is a story in Norse mythology where they are believed to be reflections of the shields of the Valkyries racing across the sky on their way to their resting place in Valhalla. And another popular mythology is in Finland, where it's believed that the Aurora Borealis is caused by a firefox who ran so quickly across the snow that its tail caused sparks to fly up into the night sky, creating the actual aurora. In fact, the Finnish word "revanchelet" is specifically unique to the word foxfires for that very reason.
Interesting, very interesting.
I've had a lot of people, in fact, even from Finland, who know that word really well. It wasn't until about the 1790s that there were actual scientific experiments determined to try to figure out at what point in the air, in the atmosphere, were these taking place, because a lot of people thought they were much, much lower in the atmosphere. But the English scientist Henry Cavendish made the first quantifiable observations. He used triangulation to estimate that the aurora light was produced 60 to 70 miles up. And like I say, that was a lot higher than people thought. It wasn't until 1892 that the first photographs of the aurora could actually be made. And that, as you could probably well imagine, Don, was because photography was, not a very precise science. It wasn't real sensitive.
Right, you had to wait for that progression of the state of the art to be able to do that.
Yeah, I mean, the emulsions just weren't sensitive enough to low light conditions. But they still were able to get a good enough shot here from Norway so you could see a hint of the rays and spikes. In 1902, though, there was another scientist named Christian Birkeland, a Norwegian physicist. He concluded from his Tarella vacuum chamber experiment that auroral light was caused by currents flowing through the gases of the upper atmosphere, which was the first time we were getting the science right, He would show that it was that excitation of molecules up in the upper atmosphere, which is, of course, what makes neon lights work.
Exactly. Yeah, you're fluorescing a gas, basically. Yeah. So people wonder, we just mentioned, the gases being fluoresced. Is that the only cause for the northern lights?
So, that leaves out the question, what is it that triggers that in the first place? I mean, if we've got all of these high energy particles up there exciting the gas, where are those particles coming from? Well, it was in the 19th century that scientists began to notice a connection between storms on the sun and the appearances of aurora. The sun has sunspots, those magnetic disturbances that go through an 11-year cycle.
Sure.
Well, these magnetic disturbances on the sun, where the solar plasma follows magnetic loops going up and down from the surface, well, sometimes those magnetic field lines can snap. And when they do, violent eruptions can release vast amounts of charged particles out into space at like 5 million miles per hour.
The solar wind, right?
And it gets carried by the solar wind, exactly. Well, it just so happens that we're heading into the start of a new sunspot cycle. And so the next maximum is coming up in 2025, or at least that's the projection. But sunspot numbers are already on the rise, and that means auroral activity is starting to increase. Well, how does that cause the aurora? Two things. The Earth has both a magnetic field and an atmosphere. The magnetic field, of course, is produced deep inside the Earth's interior. The outer core is liquid iron and nickel, and its convective movement against the solar inner core, the solid inner core, acts like a generator, and that creates a magnetic field that surrounds the planet. So, like you mentioned, the solar wind, when the charged particles of the solar storm are carried by the solar wind, they could reach the Earth and get trapped in our magnetic field. Some of the particles are deflected around the Earth, but others are funneled into the polar cusp, where they're directed toward the north and south magnetic poles. And as they come rushing down into the atmosphere, there's where they collide with atoms of oxygen and nitrogen, causing them to fluoresce and glow like a light bulb. And of course, what does that mean? Ta-da!
The northern lights. Yes.
The Aurora Borealis, for those of us in the high northern latitudes, or Aurora Australis, if you're in the extreme southern latitudes. This video was actually taken from the South Pole Research Station, but they can be seen, there it is, from the southern tips of several countries. And you notice how bright and prominent they get as you get closer to the geomagnetic poles.
Exactly. Those greens and reds and magentas were quite vivid. Now, I suppose there are better places to see the northern lights. I'm thinking maybe the equator is not one of them.
Yeah, the equator, unfortunately, is definitely not one of them. And one of the reasons we refer to them as the northern lights is you have to either look really, really low into the northern horizon, or you can see them higher up in the sky if you just happen to be at the right latitude. Now, a lot of times we've heard, well, shouldn't the best place be right on the pole itself? Actually, no, they're not on the pole either. The best place is actually around this ring, if you will, that surrounds the geomagnetic pole. And what's happening is all those particles are coming rushing down through the cusp, and they're coming down into a kind of a funnel. And the auroral oval is the best region to be. That's generally between 60 and 70 degrees north latitude for the northern hemisphere.
Okay, so this relates to the magnetic North Pole and not the actual North Pole.
Right, so not only is you don't need to be on the North Pole, you don't even need to be exactly on the geomagnetic North Pole either. You want to be in that auroral oval that surrounds the pole. And so what are we talking about? Northern hemisphere, that would be Canada, the Yukon, Northwest Territories, Alaska, and then around to the other side would be northern Siberia, northern Scandinavia, southern Greenland, and all of Iceland, which is probably why you see a lot of pictures from Iceland, right?
Exactly.
Well, if you're in the southern hemisphere, the geomagnetic pole and the auroral ring for the southern hemisphere actually mostly just covers Antarctica and a huge swath of the southern Pacific and southern Atlantic Ocean. But if storms get more violent, then they will stretch up higher. So what do we mean? What are the different levels of storm activity that you can have? They can stretch further in latitude. In other words, further down into the southern United States, if the geomagnetic activity goes way up, and that's when we would have what's called a storm. You probably heard of these factors called either the KP index or the G. The G
Yes.
indicates, yeah, go ahead. The G means you've actually got a geomagnetic storm going on, and that's what you're looking for. If it's a KP index, that means, it could be anywhere from just a little bit of background all the way up to an intense storm.
Now, looking at these numbers, I would think that they would relate to the severity of the material or the quantity of material ejected from the sun that we talked about a little bit ago.
Absolutely. So you have not just a higher density of those charged particles coming from the sun, they're also coming in faster and with more energy. And so that's what determines how high up the chart it's going to go. So for example, using those different indices, if you had a really intense storm, say KP9, you notice how far south that geomagnetic storm can go. In fact, back in 1989, there was a KP9 so intense, people saw it in Florida.
Oh my.
And I know, I was living in Florida in 1989 and saw them myself, and everybody in the state was freaking out.
I would imagine, yeah, rare occurrence indeed.
Front page news. But something to keep in mind though, and this is really important, the northern lights can be notoriously unpredictable. A prediction is not a guarantee because there are so many changing variables in the geomagnetic storm itself. So it's better to look at predictions rather than alerts, because alerts may only last for a while, and by the time you hear about them, the storm has probably already passed. So it's better to look at predictions and then go out and see if it happens.
Okay.
If we take a quick look at the southern hemisphere, you see what happens and how far it'll stretch. When you get a really strong storm, they can occasionally be seen as far as King George Island or the southern tip of South America. Or if you're around on the Australia side, New Zealand, Tasmania, and southern Australia. So they will get a chance to see them if the storms are strong enough. There's also some of them that are mapped into color scales. Like a moderate storm C is in green and only stretches down so far, but let's compare that to a violent storm where major activity is marked in red. And notice here how much farther the storm is reaching. It's actually getting down close to part of the Great Lakes.
Exactly. Mike, this has been a fascinating discussion, but we do have to fit in a break. If you've got a question, send us an email. The address is down at the bottom of your screen. And coming up next with Term of the Month is Stephen.
Thanks, Don. The term of the month is Classical Nova. A new binocular classical nova has appeared as of March 19th. This image is courtesy of Ford Club member Doug Bach. It's near the 5th magnitude star 4 Cassiopeia and open cluster Messier 52. Cassiopeia circles close to the North Star, but is currently near the horizon at night from Michigan. A classical nova happens when a white dwarf star orbits another star so close that they touch, and the white dwarf pulls material from the larger star. This new material heats up and ignites as fusion, therefore brightens. The white dwarf isn't destroyed, and the process can repeat. The previously known star at this location is a known eclipsing binary. However, neither star is a white dwarf. They're both main sequence stars. The permanent IAU name is V1405 Cas, and that's Classical Nova, the term of the month. Back to you, Don.
Thanks, Stephen. We're here with Mike Murray, planetarium manager and astronomer at the Delta College Planetarium in Bay City, Michigan, and we're talking about the Northern Lights. So Mike, continue on.
So if you happen to be in one of those zones that we were talking about during a geomagnetic storm, what are the different ways you can expect to see the Northern Lights? Because they can happen in a number of different ways. Most often, the way they begin is as just a very subtle glow on the horizon. Many people have probably seen them, but assumed it was a glow from a far-off town. You might not even notice any color at first, but if you do, it's most likely going to be a pale shade of green. Over time, you need to watch for gradual changes. In particular, look to see if the glow seems to lift off the horizon into a strip that's roughly parallel to the ground. In other words, you'll know it's the aurora if it appears above the horizon with a sharp border at its base. From there, the display may or may not erupt higher into the sky. If it does, there are some features to look for. Here, for example, is considered a curtain aurora. Watch for slow and subtle changes in brightness and shape, because it may not move as fast as some of the time-lapse photography that you see. And by the way, keep in mind that these are time exposure photographs. To the naked eye, they won't appear nearly this bright, and the color will be muted, but strong storms will make them more obvious. Other features to look for would include spikes that seem to slowly grow and fade, sometimes with different colors. Other similar displays are called rays, these longer streaks. And one of the nice things about being right under the auroral oval, if you're way up in those northern latitudes, is that during a strong storm, the northern lights can seem to appear higher up in the sky. And they might even produce what are called coronal displays, meaning right out of the zenith, the top of the sky.
Interesting.
Here's one of the things that I really love to watch for if you're way up in northern latitudes. You see the shimmering going on.
Yes.
Well, during a really strong display up higher, up north, they can occasionally cover the entire sky all the way down to the southern horizon and display here what's called shimmering. This is actually sped up somewhat because it's taken from a series of time exposure photographs, but you really do notice what seems to be like a shimmer that goes all the way down to the horizon. I've seen it from Montana, and it was incredible. I couldn't believe how obvious it was.
So the question on the screen says, what causes the colors? So that's a good follow-up to, we found out what caused them, the charged particles from the sun, but why do we see those colors so we can tell that we're not looking at the zodiacal light versus the northern lights?
Yeah, so the zodiacal light will seem to stay stationary. The aurora will very slowly change in color and maybe even in shapes, bright patches. But there are other colors besides green, and it all depends on the speed of the charged particles, the atoms that they strike, and at what altitude. So for example, above 150 miles, it's the oxygen atoms that are glowing red, because at this height, the oxygen is less concentrated and is excited at higher energies than the denser oxygen lower down. By the time you get down to 60 to 120 miles, that denser oxygen is what gets excited and comes out green. That's the most common color, and that's because your eyes are also most sensitive to green. Now, some people have reported blues and purples. Those are really rare. They tend to appear only when solar activity is high, and it's a reaction with nitrogen that causes the blue and purple, typically at the lower end.
Okay, because the nitrogen would be closer to the surface than the oxygen, and hence that's where that would happen, and would take a stronger storm, I assume, to be able to excite the nitrogen at a level closer to the Earth?
Exactly, because imagine all the energy it would take to penetrate that far down into the atmosphere and still have enough energy to excite those nitrogen molecules. So yep, you really need high energies. So for example, here you see the different levels of colors. The red way up high, that's 150 miles up. And that's one of the reasons why, if you're way farther south in latitude, red might be what you see because it's so high and can be seen around the horizon. Here's a great shot of what some of the blues and purples might look like at the lower levels, maybe only 50 or 60 miles up. You can even see the color differentiation from the International Space Station, especially the greens and reds. And the astronauts have taken great images and time lapse from orbit. And here's just a few we'll let you look at.
Well, these are gorgeous.
So having that cupola module is just amazing. So,
all right, so we've seen the colors and we understand how the colors happen. We've covered, where we need to be, either at the top of the world or the bottom of the world. And but what are some observing tips?
These are the things that I always like to put out there because there's a little bit more to it than just going out and looking north. Before you even go to try to find aurora, you've got to be able to ask yourself some questions like, is there a solar storm strong enough to trigger a display right now? Is the KP index strong enough to reach your latitude? And you, of course, want clear skies, but humidity can create some horizon fog. So things like that you want to take into account. Make sure you don't have horizon glow from a nearby town in the north, and no moon, because you'll need it to be as dark as possible, right?
Exactly.
Some of the forecast sites that I like to use come from NOAA, the National Oceanic and Atmospheric Administration. Mm-hmm. And there are some other really good sites here that will give you very good predictions. Now, again, they're only the likelihood. Just because there's a strong prediction doesn't mean it's definitely going to happen. People have often asked me, are there webcams? And there are. A lot of them will do photos, but some of them do live video as well. And the list will look like this when you go to that link. But then this is one of my favorite links to go to live aurora. If it happens to be clear, and it's, of course, wintertime most often, is when it's dark up there that far north. This is a good cam to look for.
So, best time of the year, anytime?
We get that a lot. And the thing about the time to look, it's actually by far the biggest factor is whether there's a major solar eruption taking place. During times of normal baseline activity, it seems like spring and fall seem to have a few more displays on average, but it still depends mostly on the activity of the sun. If there's a best time of night, if it's just a regular baseline event, best is like between 11 p.m. to 2 a.m. But if there's a major storm going on, go out and look anytime, as long as it's dark out, of course.
Very interesting. Yeah. So here's the question that I wanted to have answered. Can you hear them?
There was a lot of controversy over whether or not you could actually hear the aurora, because a lot of scientists said, well, the aurora are taking place anywhere between 50 and 200 miles up. You can't hear that. So what was the physical mechanism? It turns out there are sounds that have been recorded, and I don't know if you can hear this, but these are actual recordings that have been amplified.
Okay, I can hear that quite clearly.
Yeah, you hear the static. It's almost like static discharge. It turns out, while the sounds are connected to the aurora, they're not generated up there at the source. These are sparks of electricity that are discharging beneath the aurora in an inversion layer of the atmosphere. And so you know how temperature inversions can happen when there's a blanket of warm air above the cold air next to the ground? Well, the sounds are caused by the buildup of electrical charges in the inversion layer, which may only be about 250 feet up.
Interesting.
And so it's those electrical discharges that build up and then can get released because of the aurora. So yes, there are electrical discharges that can be heard, but it's actually in the inversion layer.
That's fascinating. I'd like to thank our guest, Mike Murray, for this really interesting talk about the Northern Lights. We'd like to have you visit our club website. The address, as always, is down at the bottom of your screen. And coming up next is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for April 2021? Here in Michigan, the nights get shorter by 79 minutes over the month of April. The last quarter moon is on April 4th, the new moon is on the 11th, the first quarter is on the 20th, and the full moon is on the 26th. All of these images are on the 30th of April. At 1 hour after sunset, Mars has gone to Gemini from Taurus, is at the foot of Gemini near some easy clusters. An hour before sunrise, Jupiter has left Saturn in Capricornus and joined Neptune in Aquarius, while Pluto is in Sagittarius. On the 30th at sunset, Venus is literally in the trees at sunset. Superior conjunction was the 26th of March, and this is the best we can do. Mercury has superior conjunction on the 18th, and Uranus has superior conjunction on the 30th. And so neither are really visible. And that's what's up in the night sky for April 2021. Remember, we don't charge for this show, but we may tax your brain.